Swayam Prabha. Digital India. Educated India.
So the next part of this talk is recursive identification. If we have data from a process, let's say we have past measured values of the output and the input, the question is, can we estimate the coefficient of the model? So here, remember, we had the model as y of t is equal to a1 times y t minus 1 plus b1 times u t minus k, where k was the time delay. This can also be written in the form a1 b1 times y t minus 1 and u t minus k. So this term is theta transform and this term is phi. This is a 1 by 2 vector and this phi is a 2 by 1 vector. Now remember, there is a difference. This is lowercase phi, whereas the uppercase phi that we used, this was a n by 2 matrix. So there is a distinction. This is a lowercase phi, it is simply a vector, 2 by 1 vector. So we are saying y of t can be written as theta transpose times phi. So let's say we have n observations. N is a large number. In other words, we have recorded y at time t, t plus 1, t plus 2, all the way up to t plus n. N can be thousands and thousands of variables. Given all of this data, and also we've recorded the input values, given all of this data, can we estimate the parameter coefficients a1 and b1? So to do this, we form what is known as a loss function. So we would like to describe the loss function j subscript n corresponding to the number of observation. It is a function of theta, and j is equal to 1 divided by n, the summation of e t squared. This is the sum of the squares of the errors over the entire n length time interval. The error is the value of the measured output and theta transpose times phi, as I explained here. Okay. So this is the measured output, and here is what we would be able to predict if we had the coefficient. So we would like to minimize the sum of the squares of these errors. Now before we begin, I also want to show you something else. Remember, we had the expression y was equal to phi times theta. Given this equation, and recall this was n by 1, this was n by 2 matrix. This is a 2 by 1 vector. Given measurements in y, given all the measurements in the matrix phi, which is an n by 2 matrix, can we compute theta? Ordinarily, if phi is a square matrix, then we would be able to simply say theta is the inverse of phi transpose times y. But phi is not a square matrix, so it is not invertible. But if I multiply both sides by phi transpose, I get phi transpose y equals to phi transpose phi times theta. Now this becomes a 2 by 2 matrix. It is a square matrix. If there is enough excitation in the input, it is also likely to be in an invertible matrix, and therefore theta, the estimate of theta will be phi transpose phi, its inverse, multiplied by phi transpose y. So this is what we call a batch least squares estimate. Okay? So be aware of all of this. Okay, so let's. So now, if we look at this expression, we want to minimize the sum of the squares of the prediction errors from t equals 1 to n. Let's expand this term. So y t minus theta transpose phi squared becomes yt squared, and then this term squared becomes this. So y times theta t twice gives you this expression. This term squared is as shown here. The derivative of j with respect to theta. Now remember this, ordinarily this is j with respect to a1 and j with respect to b1. So that's what you get here. This is a 2 by 1 vector multiplied by y. Phi transpose, again this will be 2 by 2 matrix multiplied by theta, so it becomes a 2 by 1 vector. So the partial derivative of j with respect to theta from here gives us this expression. And of course we want to make this equal to 0. The derivative has to be 0. The partial derivative, if we want to minimize the sum of the squares of the errors. So multiplying this by the summation sign, the multiplier 2 over n doesn't matter anymore. So when we do this summation expression, this sigma times phi transpose theta, take this on the left hand side, this is equal to phi y of t, and this, I'm sorry, this term here is exactly the same as what I had written earlier. This is the batch least square solution. In fact, theta hat is exactly this as we derived. All right. So this is exactly the same. If you multiply if you put all the terms inside the matrix, it is exactly this term. Now, the question to ask is, what do we mean by batch least squares? You've collected n observations, capital N observations, and you obtained an estimate of theta. But what if you have only 200, 300 observations and you're collecting data online, and you want to continue to update your model as you collect more and more data? So this is what we mean by recursive least squares. As you start with the fewer data points, but subsequent, so you start your estimation procedure as soon as you have enough points, but as you continue, you will have more and more data points, and you want to continue to update your model. So that's what we mean by recursive least squares. So to obtain recursive least squares, we first define the matrix PT inverse is the summation of phi transpose. Okay. Actually, it turns out PT inverse is this term here. Then from equation 1, this equation here, theta hat at time t, remember we're trying to now turn this batch least square solution into a recursive least square solution. So theta hat at time t is from k equals 1 to time t. We've collected now t sample observation. This is equal to phi k transpose, exactly this term here, times from k equals 1 to t phi of k times y of k. This expression is as shown here. So that's p of t times summation phi k times y of k. Okay. So let's now, the last equation is pt. It was theta t is pt on the right hand side, but we can bring pt minus 1 on the left hand side, can be written in this form. So pt inverse times theta hat t equals to summation k 1 to t phi of k times y of k. Therefore, theta hat t is pt. It's exactly this expression that we obtain. Okay. So this is telling you, when you collected t sample points, the expression or the estimate for theta hat denotes the estimate. The cap that we have denotes it's the least squares estimate. It's not an exact number, meaning it's not the exact value of that you would get from the model. Based on t points, it is an estimate, is equal to p of t summation k from 1 to t of phi k times y of k. This term here, from this expression here, expression 4, can also be written as from the summation from k equals 1 to t minus 1 phi k y k plus this term is exactly this, right? And by using equation 4, theta t, we can substitute we can change the summation sign from k equals 1 to t minus 1 and substitute this here. So we would get pt times pt minus 1 to the inverse minus 1 times theta hat t minus 1 plus 5 times y of t. Okay. Because by definition because pt inverse is this term, we can write it in this form. So look at this expression, pt minus 1 is this, which is pt minus 1 inverse plus 5 phi transpose. If you substitute for pt minus 1 from equation 6 into equation 5, we put this, all of this into here, into this term, this expression here, we will get the following expression, and this is important. So the estimate at time t is pt bracket pt inverse minus 5 phi transpose bracket close times theta hat time t minus 1 plus phi times y of t. When you multiply through pt times its inverse times theta hat t minus 1, we get this expression, and then this times this phi transpose as shown here, phi transpose theta hat t minus 1. So rearranging this expression gives you this simple equation, and this last equation can be written as theta hat at time t, the estimate of the parameters at time t equals to the estimate of the parameter at time t minus 1. So the new estimate is equal to the old estimate plus p times phi, some measure of the gain, multiplied by y minus y hat. This term here is the predicted output at time t. It is phi t minus phi t transpose times theta hat t minus 1. So it is the predicted output based on the estimate that you computed at the previous interval. So y t minus y hat t is the error between the measured output and the predicted output. So this equation reads, and this is the recursive equation, reads the new estimate is the old estimate plus the gain times the prediction error. We keep on doing this as you get new measurements available. You get new measurements available, we will update the estimate. Look at the old estimate and find out the prediction error multiplied by the gain, which is p times phi, and obtain the new estimate, the updated estimate based on the newest measurement. Okay. So let's summarize this now. So summary of the RLS algorithm. Here is what we derived just a few minutes ago, this expression, but this expression needs p of t, and p of t is related, well, the inverse of p of t is related to the inverse of pt minus 1, meaning the information matrix or the covariance matrix at the previous instant plus phi transpose. So the steps are update pt minus 1, compute pt, solve for theta hat of t. The problem is each step in the recursion requires the inversion of this matrix. we compute pt minus 1, but this update equation needs pt. So we have to invert this matrix to obtain p of t. Matrix inversion is somewhat time consuming. So in order to simplify this, we use the matrix inversion lemma. There is a statement from Leung and Soderstrom's book, which says, let A, B, C, and D be matrices of compatible dimensions so that the product B, C, D and the sum A plus B, C, D exists. If that is the case, then the inverse of A plus B, C, D inverse is this expression here. And you can prove it by showing that A plus B, C, D multiplied by A plus B, C, D inverse is an identity matrix. We won't go into the detail. Now there may be a slight typo here. There is a minus, an inverse sign missing here, and I will clarify that a little later. So let's apply the matrix inversion lemma to the covariance update equation. Let's apply the matrix inversion lemma to this update equation. Remember, this update equation says the following: the covariance matrix at time t is equal to the covariance matrix at time t minus 1 plus phi transpose. Let A be equal to this term here, let B be equal to phi of t, let C be equal to 1, let D be equal to phi transpose. So remember, the term BCD is also of compatible dimension to A. So now we want to obtain, in terms of phi C1 and phi transpose and pt minus 1, we would like to obtain an expression for p of t. P of t is therefore A plus BCD inverse. If we go to the next page, then pt is shown at the top. So this is the term minus 1 that was missing in the matrix inversion lemma. So make sure you take that into account. So if I want to compute pt, it is A inverse minus A inverse B times this expression. So if you plug in the values for A, B, C, and D, here is the expression that we get. So pt is the previous pt is the p at time t minus 1 minus pt minus 1 phi transpose pt minus 1 divided by this term here happens to be a scalar. So scalar inversion is easier than matrix inversion. It is 1 plus phi transpose p t minus 1 phi t. So the covariance update equation requires a scalar inversion. Compare this to equation 8 in a paper, and I'm going to also have this paper uploaded and be available with these set of slides. So the summary of the recursive least squares algorithm is: update the covariance matrix using this expression, compute the gain matrix, which is p times phi of t. This is the vector gain matrix. So here is p, multiply all of that times phi of t. So the gain, if I multiply through this expression, simplifies to this here, and then I compute my new estimate. The new estimate is theta hat at time t equals to theta hat at time t minus 1. The new estimate is the old estimate plus the gain times the prediction error. P times phi is k as explained here, multiplied by y minus phi transpose theta at t minus 1. So the algorithm is as follows. Start with an initial value and an initial value of the covariance matrix, and then at time t plus 1, that is at the first sample interval, solve for k from equation B, solve for theta hat from equation C, and then compute pt for the next time from equation A. Here, equation A, and at the next sample interval, increase t by ts and repeats from step 2 onwards. Okay, so there is a do loop here, and that do loop is here. Okay, so let's apply this. So just to repeat, the generic form of this estimation law, and this is the for recursive estimation or recursive update, this is always the case. The new parameter is equal to the old parameter plus gain times a regression vector consisting of some function of past values of plant output and input times a measure of the objective error. In this case, it's the prediction error. And I write here all estimation laws, be they maximum likelihood or stochastic approximation, all have this form. All estimation laws have this form. Let's apply this to this example. So the example to illustrate the performance of first ordinary least squares or batch least squares and its many different variants. Okay. So here is y of t equals to a y t minus 1 plus b u t minus 1 plus e of t. So there is no delay term in this example. The correct or the true value of a is 0.9. Then the value for b is 0.1, and we change the value of b. For the first 499 sample intervals, b is 0.1. Then for the remaining 100 intervals, sample intervals from 500 to 600, b assumes a value of 0.5. If you look at the gain of this process, the gain of this process initially is 1, but from instant 500 to 600, the gain becomes 5, so becomes significantly larger. The input that we, in this simulation that we conduct, we were putting in what is known as a pseudo-random binary sequence. It is like white noise. The mean value is 0, and it has the magnitude plus minus minus 1. So it's either plus 1 or minus 1. You could also have the input as a random binary sequence up to for the 600 sample instance. We also add some noise to the process. ET is Gaussian noise of variance 0.02. This corresponds to some sensor noise. Our initial values for the parameter are 0 and 0, and the initial value for the covariance matrix is just identity terms, 1 and 1. Okay. Let's go to the application. So here is our process output. The process output y in the simulation is just this time series, and notice when the value of b changes from 0.1 to 0.5, the gain increases by a factor of 5, and the output also gets multiplied by that number, so it becomes significantly larger. So this is the output, and for batch or ordinary least squares, if we apply the algorithm that we've just developed, start at time t equals to 1, and as you get more measurements, 2, t equals to 2, 3, 4, 5, compute the estimate. And what I'm showing you here is the estimated value divided by the true value. Okay, the estimated value divided by the true value. So you ideally, if the estimation is going to be perfect, you want these values to go to the number 1 as soon as possible, but that's not the case. We do get one of the parameters go closer and closer to that value, but there is somewhat of a bias, so we don't get an exact estimate of the parameters that we would have hoped for. And that's the reason for that is the algorithm that we've just developed goes to sleep. The algorithm cannot track time varying parameters, and our parameter changes from b equals 0.1 to 0.5, and there is a big gap here between the true value and the estimate. So what can we do? And the reason why the algorithm cannot track the values is because the covariance matrix P decays to a very small value. Now, the covariance matrix is a 2 by 2 matrix, so you can't plot the values of the covariance matrix, but what we can do is plot the trace of P, meaning the sum of the diagonal elements of P. And those diagonal elements, remember the initial values were 1 plus 1, 2, and it decays very quickly down to a small number. And because P decays to a small value, remember the algorithm was this gain K. And this gain K is P times phi. So if P becomes very small, the gain becomes very, very small. So no matter what the prediction error, the updates will not occur. So in order to alleviate this, what can we do? So P decays to a small value. So what's recommended is that because the covariance matrix decays to a small value, here is the covariance update. The new covariance matrix is equal to the old covariance matrix minus this term here. This is the correction or the update term. This term is always positive due to persistence of excitation. The input is always changing, or it could be 0 if there is no new excitation, no new information when the process is at steady state. So if this term is always positive, then you're always subtracting some positive term from the old covariance matrix, and it quickly decays to a 0 value. So ordinary recursive least squares algorithm does not retain alertness or adaptivity. It cannot track changing parameters, and we say the RLS goes to sleep. So let's look at this in figures 1, 2 and 3. Well, I think we already did look at, this is figure 3 and figure 1. So we're going to now change let's modify the algorithm slightly. To retain alertness, we introduce something known as the forgetting factor. It's a term lambda, a number less than 1. And so here is the modification. Instead of simply minimizing the sum of the squares of the error, here is the summation term, we multiply this term lambda to the power n minus t. Remember, lambda is a number less than 1. So when n is large, okay, in the beginning t is a small number, n is large. So when lambda, a number less than 1 to the power a large number, will quickly become very small. However, when t approaches n minus 1 or n minus 2 and so on, so in the beginning, the all values, when you are looking at the beginning values of the prediction error, they do not appear significantly in the loss function. The more recent values of the output and the corresponding prediction errors carry a slightly larger weight. So this term significantly helps. And when you do the minimization, the result is the gain matrix K and the covariance matrix update are modified with the term lambda in the denominator here, lambda in the denominator here and here. And the choice of lambda is important. A small lambda, a very small lambda, remember lambda is less than 1, but a very small lambda will discard the data very soon. P and K will become large, and it's of course good for tracking fast parameter changes. On the other hand, if you have a large lambda very close to 1, 0.999 for example, it will be difficult to track fast parameter changes. So let's see how we can change this. So the recursive law becomes theta hat is equal to theta hat t minus 1 plus k times y minus phi transpose phi, and here is the gain update, and here is the covariance update with lambda as I showed you earlier. So here is the application with the choice of lambda equal to 0.9. As compared to the previous figure 3, we are now able to track the parameters fairly accurately, although there is some variability in the parameters, and we say the parameter variance is somewhat large. When the gain of the system becomes 5, we get exact tracking, which is a good sign. Okay, so this modification that we made is able to track changing parameters as shown here, and because of higher gains, the variance of the estimated parameters is higher, and that's what I'm showing here. The variability in the estimate is a little high, so the estimates are somewhat noisy, noisier than you would like. Well, what can we do? Look at the trace of the covariance matrix, and the trace now is changing significantly. However, the trace becomes small here, so it may not be able to track more changes if they were to occur here. So P becomes small in the interval from 500 to 600 under rich excitation. Okay. So let's see what we can do again. So this is where the engineering comes in. You want to develop an algorithm that is going to allow you to track the parameters accurately and with low variability. The main difficulty in exponentially weighted recursively squares is when the information content in phi is small. When there is no excitation, then phi times y becomes 0. The covariance update becomes just this term here, and P now grows exponentially fast, and so does K. This is known as covariance wind up or blow up. Consequently, any small changes in phi, for example due to noise or process upset, will cause large parameter fluctuations, large changes in the estimated parameters. And so we say exponential forgetting leads to covariance wind up or blow up. So let's see figures 5 here. So here we converge, and suddenly the variability in the parameters becomes very large. So parameter trajectories for an RLS algorithm with lambda equal to 0.9 with no process excitation in this interval. So suddenly in this interval 200 to 400 we have no excitation, and the covariance matrix becomes large, as we shall see in the next slide, and this leads to large parameter variance or blow up here. The trace of the P matrix becomes very large, as you can see here. No excitation, the regressor is very small. We have a covariance wind up. P becomes very small in this interval, also in the interval 500 to 600 under rich excitation. Okay. Again, as engineers, we make changes, and so one idea is to try and get lambda to approach 1, be close to 1 when the prediction error is small. In other words, we say there is no need to update. The prediction error is within bounds, it's acceptable, let's not play with the update. Otherwise, when the prediction error is large, we make lambda significantly smaller. So here is the expression for lambda. Lambda now becomes a function of the prediction error. This is the prediction error. When prediction error is very small, lambda will be close to 1. When prediction error is large, we will subtract a relatively larger number from 1. This is normalized, so it will end up being a lambda value of less than 1. Here is the corresponding update equation, same as before. So, and we also need this additional mechanism. We have this weighting matrix W to ensure that P remains bounded. It does not become unbounded. And for that we say Pt minus 1 is this update divided by lambda t minus 1. Okay. So, in other words, this is to ensure that when lambda is less than 1, pt will be large. So if the trace of w divided by lambda is less than c, we enlarge, we make p larger. Otherwise, p is simply equal to w, which means lambda is effectively equal to 1. So let's see the results of this change, these changes. What this does, it preserves alertness or adaptivity, and it works quite well, as we shall see. So now, even when the gain of the process is small, we are able to very quickly estimate the correct true parameters, and the variance of the parameters is relatively small. And when the gain becomes large, there is a good, in large excitation, we are able to estimate the parameters very accurately. Okay. Here is the forgetting factor lambda as it changes with the expressions that we have developed. And when the large change occurs, there is a big change in the forgetting factor lambda, and it quickly gives you the adaptivity that we seek. So basically, this algorithm that we developed here does work, and this is the algorithm that we will demonstrate the use of in the adaptive application that I will be able to share with you. Thank you.